So there are some simple calculations now we will be doing, which will be telling us certain scaling relations, which plays a very important role in, because the size is so big, and since there are so much correlations between these polymer chain, it makes sense to talk in terms of certain very simple to find out how different properties of the polymer scales with the size n. Like we already found that the size Rg scales as n to the power half. But now that is when polymers, the monomers don't interact at all. However, in a real world, the monomers interact with each other, particularly when they kind of a collapse state, like in protein or in many other polymers. In a polymer in a pore solvent, they collapse, and that means it brings a little bit of the structure of liquids. It brings to us I have to talk of local correlations, I have to talk of the local density and local volume, but however at the same time I do not want to give up the beauty or that this scaling relation that polymer is famous for, and that polymer really works. So the large size of the polymer at the same time can be again exploited to get these certain ideas about the size. So in the Gaussian chain polymer, the freely jointed chain polymer, that fluoropolymer. So these are all the same name, that fluoropolymer, then Gaussian chain, then freely jointed chain. These are all Gaussian polymer. These are all the same things that we talk about. That so it is essentially means that monomers don't interact with each other. So one of the major thing of that so this kind of thing, so this is allowed. So this is allowed. This is allowed. So as a result, in a freely jointed chain, all these crossings are allowed. That and that means no volume is excluded. So no volume is excluded. But real world, of course, you cannot do that. In real world, you cannot do that. This is not allowed. This is not allowed. Okay, this is not allowed. It might seem that it is a small thing, but no, these excluded volume interactions, that some volume is excluded, plays a very important role. But how do I talk about it? At the same time, I don't want to talk of completely the probabilistic description, because this is a many body system which has lots of randomness. That brings us very close to the concept of liquids. So the concept that we developed in theory of liquids, like distribution function we already used, which is like the distribution function of liquids, but also the concept of density and arrangement, nearest neighbor arrangement. These kind of things can be used in polymer, and that is what we are going to do next. So, and that is done by saying, okay, that we know this, let us see Gaussian chain, but number of monomer contacts, we are now going to talk of monomer interaction. Number of monomer contacts between two things are can be shown. I had a DA of that, proof of that. I don't know why that disappeared. Okay, so number of contact, phi star is the number of contact. So number of contacts is phi star, number of contacts is phi star, and it can be shown that number of okay. So 5 star each is the 5 star where each monomer, the number of contacts made by each monomer. So then N5 star, so number of contacts made by, so this was in my notes, but I don't know what happened by, okay, each polymer, each monomer is 5 star. So total number of contacts, the N monomer is N5 star. This is very, very important, and I will just show you how important it is. Okay. 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 Yeah, this is not should be here. So probability of a given monomer, probability is 5 star that a given monomer encounter another monomer. So this is not the number but probability, but we are going to the number from that. So if how would that come? It will come because it will be just like in liquid state, that there is a volume of a monomer, just like in liquid state I have a volume of a monomer, just in liquid is a volume of a monomer, and then the volume of the monomer, which I can take like that with excluded volume, then the number of molecules there, the contact within the same in liquid state in a shell will be the density. So then density of my polymer, average density of the polymer, which is same as the density of the liquid, analogous quantity, is total number of monomers divided by the volume of the monomer. So volume of the monomer R to the power D. So in D is the dimension. This is something which is in polymer is more common now, not in fluoride. In fluoride you would have put D equal to 3 everywhere, but in a physics literature D is very popular and favorite is D equal to 4, because at D equal to 4 we get a Gaussian polymer. So one can do the calculations about dimension 4 by making introduce a constant called epsilon, and which is comes from critical phenomena in the Gaussian group, and then epsilon is D minus 4, and so or 4 minus D, and D is 3. So epsilon becomes 1, and you could do a calculation where there is a lot of fun one does, but we don't need to worry about it. So if the monomer volume B is for bead, the B that is introduced, because in physics kind of language this is nothing but a bead. Many times the chemists don't like to consider monomer as a bead, because we deal with monomers all the time, and but physicists is nothing but a bead and the necklace model. So the bead B, so B cube, B is R, the size of the bead R cube, but the R is kept for the end-to-end distance. So this is the volume of a monomer, then volume of the monomer into the density, and density is total number of monomers divided by the volume, which is R to the power D, R cube. Once we have 5 star, so we have the 5 star, and then we can show, since R equal to n to the power half, I can combine it before, and it becomes n to the power 1 by D by 2, and n 5 star, the total number of contacts in my entire polymer chain is n to the power 2 by. Now this is very interesting. For 3 dimension, then I have n to the power 2 minus 3 by 2 is root over n. So number of contacts is enormous. So again, if I take 100 million, which is a very good number, and for polymers, then 100 million means 10 to the power 8. So I have 10 to the power 4 contacts. There will be 10,000 contacts, and contacts cannot be allowed. So you immediately see that if I exclude the contacts, then size of the polymer will increase. So the simple analysis tells me the Gaussian polymer chain is inadequate. The random walk model. So what is the polymer chain are doing is nothing but doing the random walk. That's why this is the result that we get into size is same as that of a random walk. That how much a random walker will go in n step is exactly this distance is root over n, which is the size of the polymer. However, if you now make the random walker, no, You cannot visit the sites you have already visited once, you are excluded from that. Then the random walker has to take new and new sites. As a result, the end-to-end distance, the distance the random walker will go now, will become larger, and that has a tremendous implication in these things, and that we will do now. So, I go back again. So, I have considered phi star probability of a monomer is encountering another monomer, and that is monomer size is b to the power d and density is n by r d, then n phi star is total number. So, then they become n square, and then n square, and these r comes on the up. So, n phi n square and r d is root over n. So, I get d by 2. Okay. So, now then the next, let us go ahead, that the things that we have done. So, is if there is one more thing that comes in addition to this excluded volume interaction, there is another term that is very popular. So, the I want to add here, so excluded volume, because contacts not allowed. You might think it is a small thing, but it is not, because there are large number of contacts. Okay. Then another thing is a different thing, is the effective interaction that is used, and that is this thing. That means in polymer, you put polymer in liquid, then this is a very good example of saying that there is a chain, polymer chain, in a kind of or a reduced kind of a description, but it captures these things. And they say these are water molecules or ethanol molecules, because polymers are not soluble in water, so maybe they are ethanol molecules or methanol. Ethanol is a very good solvent for polymers. Now, I want to, but I am not interested in the water molecules or ethanol molecules, I am interested in the polymer configuration. However, this polymer is solvated by these water molecules, but I want to have a description where these not there, because it is too difficult to bring all this, because the polymer is so big, as I told you, 100 million monomers, a huge guy. If I have to put it in a solvent, you know what I do, want to do theory or simulation, I will have billions and billions of water molecules, I need trillion water molecules, I need, that is not possible, and also does not make sense, because they seem to, polymers seem to behave in certain way. So, the concept that came in, that one said that what happened if I could average an implicit solvent. Implicit solvent means I will remove the water molecules, behave as if it is a continuum, and then I will have interaction with these two guys who otherwise are not interacting, but they will be interacting because of the interaction, just like we discussed in liquid state, interaction, they are proceeding through intervening in molecules, just as in liquid state. And actually all the concepts of liquid state comes to polymer very handy. Then I remove the water molecules, instead I have an effective interaction between these two, which is somewhat longer distance. And there is of course this hard sphere interaction, it also interacts with short length, but in long distance there could be an attractive interaction. So, this effective interaction is the thing to find from R, but we can again look into a liquid state theory. If we can get a radial distribution function between them, GR, between this monomer polymer, then I know I can write beta is 1 over kBT WR. Then WR is the potential of mean force and is the effective interaction. Okay. So, that is the same kind of game we play, that we are removing the water molecules and we are replacing that, all the complexity are taken into account by potential of mean force or an effective interaction between them, or the indirect interaction in the theory of liquid state. We remember what we did in the derivation of Parker-Sevic equation, or direct interaction, a direct correlation function, and the indirect one, which are again goes through this potential of mean force. So, we are essentially introducing a potential of mean force. Then So, effective interaction is a very important role played, it is introduced by Florey. So, if the polymer is such that, the solvent is such that it does not like the polymer, then the water molecules from where will go away and the polymer will collapse. However, if they like, then they will be inhabited inside and then the polymer will swell. So, in a good solvent, good for the polymer, like ethanol is good for many things, then they will polymer will swell, then they do not want to cross each other. So, they will almost mimic what is the excluded volume interaction, much stronger excluded volume interaction, and size of polymer goes up, and that is a very important thing. So, good solvent is where polymer is large, size is large. However, if you put, for example, a lot of water which does not like the hydrophobic interaction, does not like the polymer, then polymer will collapse, and this is shown here, that good solvent, this is a good solvent, then water, all everywhere water molecules comes in, and then you get a swelling of polymer, very important phenomena. However, if the solvent is out, if they do not like each other, poor solvent, then it collapses. Protein folding, which is a is essentially hydrophobic collapse. So, these collapse of polymer is like is a hydrophobic collapse that is so important in protein folding. Except in protein folding, we do not have a homopolymer. What we are discussing here, all the monomers are the same, that is called homopolymer, but protein is a heteropolymer, and protein collapse of protein in a poured solvent is so, because protein folding we do in water much of the studies, or at least largely water, and there are other parts also, but that is what makes. So, when protein folds, all the inside, all the things are the hydrophobic core, like alanine, valine, phenylalanine, and outside here all the hydrophobic things. That is essentially architecture of protein, which is the polymer of intermediate size polymer. But many of the things that we learned in polymer are used in understanding protein folding and many other things. So, polymer is a very important for, because of the biopolymers also. But I want to emphasize that this the concepts of liquid state, the densities B by N by R to the power D, and then monomer contact, and all these things actually are very useful in the polymer. So, then is the important thing of the good solvent and the poor solvent, that effective interaction is repulsive, good solvent is interaction is attractive. So, we now have to think of how to describe interaction between the polymers, and that was also Florey did. So, if I have the interaction between polymers, I can do statistical mechanics. Now, I can bring in the whole apparatus of liquid state, and that has been done. So, then how do I talk of the interaction between the polymers? Okay, this is the following way. Florey used it again to develop the interactions and the evolution of the coil dimension of polymer between an. Now, this is a bit, this is not effective repulsion energy, actually effective interaction energy, that we will see that it can be both positive and negative, it can be both attractive and negative. So, interaction or effective interaction energy, that is very important, effective interaction energy, that we see. As we just discussed before, that the density or concentration, I can as well call it density rho, but concentration C is total number of monomers divided by the volume R to the power D, D is a dimension. Now, I can now make the following answers. This is just a completely van der Waals, that attraction is the, or interaction between two polymers, which in van der Waals is that exactly what the free energy contribution of van der Waals, because of attraction term, exactly. If you carry out the free energy calculation of which was given in my book, that it is half A rho square and rho is the density. So, here C is the monomer density, and so the interaction C square. Now, Florey did something amazing. Up to this is just van der Waals. C square is rho square, half kBT is introduced by hand, and newt is a parameter which is a fluoroparameter and excluded many fluoroparameter excluded volume. Now what Fleury did, he said, okay, these newt that I have can be both positive and negative. If this is, I say is wrong, is called repulsion interaction. If newt is negative, then I get attraction, and that is van der Waals. But if newt is positive, I get repulsion, and that is just the beauty. So now Fleury introduced a famous parameter again called fluoroparameter, that is exactly that quantity 1 minus 2 chi, and he derived an expression for chi later which exactly works out according to this. So when chi is greater than half, then this is negative and is attraction, but when chi is small, then it is repulsion. So monomer, this interaction parameter chi simulates when the monomers attract each other and monomers repel each other, and we know when monomers attract each other when a pore solvent. So chi becomes large in a pore solvent, but chi becomes small in a good solvent. Then the molecule monomers repel each other and they swell. This is the beauty of this description. So then one does little bit more. This interaction of this is just what I wrote down. This free energy is we just say total volume, because that is between monomer in a volume BD, total volume. If I do interaction, then I get these are interacting over the total volume, and I will get the another total volume is proportional to the size r square and c square as n by rd. So when I put these things, I get n square, as I said, I get this quantity as the interaction energy, both attraction and repulsion. So I get mainly n square by rd term. We are done in 2 minutes, and then effect through the consideration of then, however, another interesting thing is that in the polymer I cannot just swell it, because there is an elasticity that through the chain. So it's an elastic. I cannot aid too much, and then and that's a proportional to r square. There is a potential energy which is like harmonic, and that term, the elastic term, goes like r square, because elasticity, and one can show it, because this essentially comes from e to the power r square by nl square. So this elastic part comes completely very easily from the Gaussian distribution. So Gaussian chain has a preferential size, and that is an entropic effect. So this entropic effect gives rise to an elasticity, because it is a favorable size is there. If you go out from that, you have to pay. If you come close to that, you have to pay. So it is a harmonic potential. That harmonic potential is the coming of the central limit theorem, and that these two you then have to add. So you have to add the interaction energy and the elastic energy, and this is the total free energy as a size r. Now you minimize that, and you get lo and behold, one of the most beautiful result of polymer science. If you minimize that, you say df dr equal to 0, then you get r d plus 2 Fleury size Ra for r star equal to n cube, and you get r is n to the power 3 by d by 2. So this exponent that introduced an exponent that r this Fleury. So because of interaction, the excluded volume, the Gaussian polymer size r get modified to Rf, and d is 3 n to the power 3 by 5. So this goes as n to the power half. So because of interaction, n to the power half swells to n to the power 3 by 5. If I go with my n equal to 10 to the power 8, then that is 10 to the power 4, and now if I do n to the power 3 by 5 into, sorry, I have to do then 10 to the power 8, 3 by 5, then I see that it is 10 to the power 24 by 5, that means almost 10 to the power 5. So, I see a 10-fold increase, a little less, 8 actually, huge increase in the size of the polymer because of the interaction between the polymers. So, this is one of the most beautiful results of polymer science, that size of the, because of the interactions, which is the contribution of the interaction between the polymers mediated through the solvent and the elastic part. And elastic part is from the Gaussian chain, that I can model as Gaussian chain. As far independence goes, Gaussian chain remains okay, but the size now changing. So, effective interaction renormalize the size and gets to a beautiful new result, and this is for Floris A R equal to n by, this is the result. Flory is n to the power nu, and nu is a Flory parameter, nu f is 3 by d plus 2. So, Flory got everything correct. This is amazing, Flory got everything correct. Flory exponent we got, that nu equal to, this is ideal chain nu half, and that is underestimated, this error, then it goes over to nu equal to 3 by 5 for 3 dimension. And this is the some thermodynamics of solution and Fourier-Young's theory we will do in the next class. Okay. For the time we will stop, and the next, the more things, more work of Flory and beautiful work of Flory continues. The saga of Flory's contribution continues with the Flory thermodynamics of polymer solution, Fourier-Young's theory. Then we will do Sol-gel transition, was also done by Flory. So, these two will be the next class. Okay. I hope you enjoyed this beautiful class.